Hi everyone and welcome to this lecture, and in this lecture we are going to discuss about how we can see operators in infinite dimensions, because in the finite dimensions we saw that we can represent our operators that acts on some kit or a vector or a bra, and we would like to generalize this idea to infinite dimension. But as you can see, I have already written some things, and I said before we dive in, let's do some integration by parts. And the example we are considering here is something like this: a function which is a function of x prime, and there is some derivative of delta x minus x prime. And you might ask at this point why I'm doing this, because as I already told you that we want to discuss operators. So what does this has to do with the operators? I would say just do it and let us see how we can use this to our advantage, and this will be transparent in a few minutes. So as you can see, I have done some integration by parts over here, that is I integrated by parts. But before I do that, in this line over here, I use the identity for the delta function that we learned earlier, that if you have ddx of delta x minus x prime like this, you can just have it as dd of x prime of delta x minus x prime. This is the property we used here in the second line to write this and pick up this minus sign. And now what I did is that I integrated by parts, and note that obviously you will have some integration limits, but I didn't specify them, and these limits we can it will be dependent on the problem that we are handling. And so let me just write it down. Limits will be dependent on the problem that we are dealing with. So that's why I didn't specify them. And after doing integration by parts, what I see is that there is this guy over here, and there is another integration like this. And after that, in the last line, you see that I'm not writing this guy. So you might assume that I have taken this to be 0, and you are correct if you have assumed that, because what I am assuming for doing this is that in my boundaries, this function f of x will vanish. For example, take a string, a regular string that is something like this, or it might be like this. And you can see that in these boundary points 1 and 2, the function itself vanishes. All right, even if you have an impulse over here. So in physics, most of the time these are called surface terms. Let me just highlight it down. Surface terms. And with suitable boundary conditions, we can always take them to be 0. Obviously, there are some non-trivial stuff when the boundary terms are not fixed. That means by not fixed, I mean not 0. So whenever the boundary terms are not vanishing, non-trivial things might arise, but we won't discuss it here. It's just for your reference. And after this, I just perform this delta integral with respect to x prime. And if you recall from your past lecture, that is the previous lecture, that x, what this delta function will do, whatever I have over here, think of this ddf of dx prime as some g of x prime. And what it will do, it will just delete this x1 and it will replace it by x, right? That's what delta functions do, and that is what I have precisely written here. And this will be useful in a few minutes, that you will see that we are going to use some analogy to find information about some operators. So let's now dive into the discussion of operators. So we defined an operator that, let's say omega is an operator, and in the finite dimension, if you had some kit like this, it will turn into another kit like this, right? And let me just give it a name, a finite dimensional case. If you translate this case into the infinite dimensions, let's call the infinite dimensional operator D, and let's skip this F just like this, and we want to have something over here that is also a ket. And in infinite dimension, this D will be a differential operator. This D guy, that is, it's similar to a derivative. So if you act on some abstract ket F that lives in an infinite dimension, that is the function space, it will give you df dx like this. It's not a derivative of function f of x yet. To do that, we need to take the coordinate basis representation. So to do that, what you need to do, you just need to put a bra over here and take the inner product of this whole thing. And if I just write it more explicitly, it will look something like this. So whatever this ddf of df ddx of f is inside this ket, we are projecting it into the coordinate basis by using this notation, and this will be just df of x, that is the ordinary derivative of this function that you are familiar from calculus. So at this point you might ask, hey, what about an integral operator, right? I mean, why did I take the differential operator, not the integral operator? Well, if D had an inverse, that could be represented as an integral operator. So this is a very schematic way of seeing things, but let's accept it and see what we can know about this infinite dimensional operators and all that. So after you are done convincing yourself that in this infinite dimension our operators are now differential operators, can I ask, can we, let's use we, can we ask about anything similar to a matrix element of this D operator? Now at this point you might say, why I'm writing matrix, because we are in the infinite dimensional space, right? But let's think schematically, and let's say you have a matrix n cross n, and you are letting n go to infinity, so that's like infinite amount of elements. So that's the point of view that we are taking over here right now, and something you'll see when you deal with a harmonic oscillator in quantum mechanics as well, because in those cases you are actually you will be actually able to find some matrix elements, that is the matrix representations of it. Obviously it will contain infinite amount of information, that is infinite amount of entries, but it's possible, it's not impossible to do that. So that's why we are saying that, can we ask about matrix elements of this D operator in infinite dimension? And the way to go about is to, let's say I want to have the xx prime element that is denoted by dxx prime, and the way to write this would be x d x prime. These are the bases for this infinite dimensional space, this x's, and it's similar to the finite dimensional case where you had a matrix, and if you wrote as ij, it would be omega ij, like this, some matrix element. So this is a similar case. And now the question is, how do I find it? I have written it in the bracket notation, but how do I calculate it, right? So that's the next question we are going to deal with, that is, how do I calculate it? This is the next question, and let's try to see whether we can actually gain something out of it. So what we're going to do is that we're going to consider an integral that involves the derivative operator D and some abstract function, abstract vector in the function space f, ket f, and if you just do it like this, for example, D f, and this is giving you what? This is giving you this df dx get, right? And after you are done with this, what you can do, you can take an x over here to project it into the coordinate basis, right? So this will now be the function of x and the derivative over here. But we can do something more. What we can do right now is that here we are going to insert the identity operation, that is this identity that was defined through this completeness relation for the infinite dimensional space. So let's do that and see what happens. So I'm just writing the integral over here, and now I'm going to use this identity over here, and if you do that, you will have something like this, right? But this is what? This is f of x prime, right? That's what we are seeing. And obviously there is this integration measure dx prime. I'm sorry for my writing, it looks a bit messy. And now what you're going to do is that you're going to compare this equation over here. Let's call it equation 2. And you are going to compare this with equation 1 over here. Let's say this is our equation 1. If you compare these two equations, then you can easily see that this f of x prime can be written as x prime of f like this, right? And here on the right hand side, so let me just write it down again so that the whole thing picture is clear to you. So our equation 1 was, let me just use another color because I'm using way too much red. So from equation 1, you can see that if you had this ddx of delta x minus x prime, right, then there was this f of x prime and there was a dx prime, right? But this f of x prime, you could write it as ddx of delta. Obviously this derivative operation is only acting on the delta function, not the x prime, so be sure to differentiate that. And this f of x prime can be written as x prime of f and dx, and this was our equation 1. Now if you just compare these two, both of them have this projection of f along the x prime basis. Both of them have this integration measure dx prime, and finally you can see that this matrix element, that is x dx prime, and there is this ddx of delta x minus x prime. And why I'm saying that these two are equal, because both of them on the right hand side, if you just look over here, had df of the derivative of f of x with respect to x. So that's why I'm saying both of them are equal, because this is f of x, derivative of f of x, this is also derivative of f of x, so these two are equal, and by that we can make this integral and this integral equation integral equal as well. And since this f of x prime is not 0 and dx prime is not 0, we are saying that this x dx prime and this ddx of delta x minus x prime is equal. So finally we have x d x prime, that is the matrix element that we wanted to see, is just ddx of delta x minus x prime. A very peculiar and kind of confusing result, but this is what it is. And obviously you can just use the identity of the delta function. That is more convenient, is that this ddx of x minus x prime will just be delta x minus x prime and ddx like this. So I am not writing anything down over here. This means that whatever will appear over here, let's say a function f of x or g of x, it will act on the right. So whenever you see some operator like this, it doesn't mean it's acting on 1. It means it's acting on whatever the function that you are giving on the right hand side. This will be pretty important when we use the operator notation, and to evaluate this kind of things, it's always a good idea to use the test functions, something we will introduce when we learn about differential equations and all that, especially in Sturm-Liouville problem. So this is it, no matter how peculiar it seems, because this is an operator element, right? And here you just have an operator, some delta function, and here you can have a test function. You can take its derivative, and obviously you will have this delta x prime. So all of this will come in very handy when you deal with quantum mechanics. And after this kind of things, you might ask that whether we can have a Hermitian conjugate of it or the complex conjugate of it. So let's say my operator is something like this, I and the partial derivative. So can I ask what is d dagger? So this is possible through using that d dagger will just conjugate this whole thing, or instead of dagger, let's just stick with the most simple example, that is d star. So d star will just be I del del x. All right. In fact, this whole thing, that is a derivative, partial derivative, or these derivatives like this, these are not Hermitian operators, they are anti-Hermitian operators. So if you have an operator like this and you want to dagger it, it will pick up a minus sign like this. And why they're doing it, we'll learn it in the next lecture when we talk about, let me just write these things down, self-adjoint and Hermitian operators. And we'll also see how we can use the idea of test functions to actually prove this kind of identities. And you might ask, why am I bringing this Hermitian again? Because in the finite dimensional case, we said that we complex conjugate the matrix elements, and then we take the transpose of it. If they are equal to each other, that is omega dagger is equals to omega, they are Hermitian. And also a result immediately follows that their eigenvalues are real. And in the infinite dimension, we are adding this extra stuff, that is something called a self-adjoint operator. And one of the special cases of this self-adjoint operator will give us the Hermitian operators that will play a significant role when we deal with physical systems. So this will be it for today, and thank you.